Okay, got it. Yeah.
Yeah.
Okay, so welcome everybody to another edition of the IFIMAC+ICMM joint seminar series. My name is Pablo San Jose. I'm from the ICMM, and I'll be chairing the session today. And then on the other side, we have Carmen Munuera, who's also from the ICMM. She will be acting as host. And as usual, this session is being recorded and will be uploaded to our public YouTube channel after the talk. Okay, so you will now be muted throughout the talk, but remember that you can use your raise hand button to ask questions, and you can do it during the talk or at the end of the talk, no problem. Alternatively, you can just simply write your questions in the chat window, and we will read them out for you. Okay, so today we have the privilege of having with us Professor Björn Trauzettel from Würzburg University in Germany. And he will be delivering a talk on the so-called topological burning glass effect. That's an intriguing title, and I'm sure you'll find the subject very interesting. So Professor Trauzettel is a theoretical condensed matter physicist, and he holds a full professor position in Würzburg University since 2011, where he was hired in 2007. And before that, he did a number of postdoctoral stays in the groups of Professor Christoph Brüder in Basel, Professor Carlo Beenakker in Leiden, and Professor Ines Safi in Orsay, I believe. He has done an impressive amount of very influential theory work in a number of fields, particularly in graphene and topological materials. And he has published more than 170 papers, including, for example, the first proposal to create spin qubits using graphene, or the prediction of sub-Poissonian shot noise in graphene, descriptions of various topological anomalies in the Josephson effect, a series of important works in the physics of Majorana zero modes, also on the effects of interactions in edge states in topological matter. It's actually difficult to pick just a few of his works, but his trajectory has been internationally recognized and has earned him, in particular, the Gustav-Mie award from the Freiburg University. So we are very honored to have you with us today, Björn. Thank you once more for accepting our invitation. So, and I will now hand it over to you. So please go ahead whenever you're ready.
Yeah, thanks a lot, Pablo, for this very kind introduction and also for the invitation. And I'm very happy to speak in this seminar series. It would be much nicer if we could meet in person somewhere, seeing so many familiar faces from the old days. But let's hope this will happen soon. So I will talk about the topological burning glass effect, and this is a work that is based on a PhD thesis of Simon Körber, who just finished his PhD. And he collaborated a lot with Lorenzo Privitera, who was a postdoc of mine, and Jan Budich, who is a long-term, former student and a long-term collaborator, who is a professor in TU Dresden. So this is about a dynamic topological phenomenon, and let's hope this works somehow. There we go. So let me first explain what I mean with topological burning glass effect, and then we will go through it slide by slide, and I explain you the underlying mathematics and physics. So the idea is the following one, that I have a dynamic topological system. Yeah? So I have in this case, it's a spin here, and the spin is driven by two external frequencies, omega-1 and omega-2. And this gives rise to something like a quantum anomalous Hall effect in, let's say, in a temporal sense, as I will explain later. And what I mean with burning glass effect, which is similar to what is shown here in this illustration in the right corner, is that this central object does not only have its own topological properties, but it can inherit the topological properties from its environment, which can give rise to an, let's say, extended topological index. So in this sense, if I have one central spin and n-1 path spins in the environment, then the topological response, as I will show in the next half an hour or so, can be under certain conditions related to a Chern number n. So this means that let's say in the closed quantum system, which is a big system, there's a Chern number n. In the reduced quantum system, which is a small system, there should be actually just a Chern number 1. And I will explain to you how basically the non-unitary dynamics of this central object can inherit this larger Chern number. This is what we call topological burning glass. So let's start slowly, and I will present you first the outline of my talk. So I will spend quite some time on quantum dynamics in parameter space, where I will explain what is, let's say, the underlying mathematics of this time-dependent physical problem. What is the topological response in that case? How is it related to adiabatic time evolution, and in particular, let's say, corrections to adiabatic time evolution, which we call first-order adiabatic perturbation theory. Then I will apply it to the simplest system first, which is a single spin that is driven by 2 incommensurate frequencies, which is not our own work, but that was done before by others. And then I will explain 2 aspects of our own work. One we call interacting topological frequency conversion, where you have 2 spins that are driven by 2 frequencies, and then the n spin problem with the central spin, which is the topological burning glass effect. And you can, as Pablo said, you can interrupt me anytime if you have questions. So let's start with a time-dependent Schrodinger equation. So here I write a very difficult problem in general, which is time-dependent Schrodinger equation. So I have quantum state, I have a Hamiltonian, which depends on some parameters R, and these parameters in principle can also change in time. And typically, this is a problem that's difficult to solve. What is simple, or oftentimes simple to solve, is the instantaneous spectrum, which is the spectrum at a given time. So then this is a, let's say, time-independent problem. This is a time-independent Schrodinger equation, where basically time is just a parameter. And so now the solutions of this instantaneous spectrum form a complete set of states, and by these solutions you can in principle write down a solution to this more complicated problem, which is the full time-dependent Schrodinger equation, because you can expand this solution in terms of these eigenstates, these instantaneous eigenstates. And so this is written here, and it's written in a way that is, it's a typical in this way of doing it, that you basically move a dynamical phase, which is like something like a trivial time evolution of this, let's say, eigenvalue of the instantaneous spectrum into a prefactor, which is not necessary, but it's a matter of choice. And then there is some coefficients, which I call Bn, that multiply to this set of eigenstates n r of t. So now, basically, you take this ansatz and you plug it into the time-dependent Schrodinger equation, and then you get this equation, which is still exact. And in this equation, you have now differential equation for these coefficients, Bn of t. And it has 2 contributions. So one contribution is basically a set of, let's say, a part which stays in the same index n. So this index n describes the different solutions of this instantaneous Schrodinger equation. And then there is another part of the solution which contains parts where this state n is coupled to other states m, which is written here. And if we talk about the so-called adiabatic limit, the pure adiabatic limit, this means we basically exclude these transitions to the other states, and we just keep this first one. We stay within one of these energy bands. And so then you can write down, now we let us first discuss the pure adiabatic limit, and then in the next step look at the corrections that come from slightly going away from this regime. So in the pure adiabatic limit, this is now a much simpler differential equation that you can easily solve, formally at least. And this is the solution here. And in this solution, there enters something which we will call a geometric phase. So this now is an expression which connects this instantaneous state with the change of this instantaneous state in some direction. And it goes from some initial time to some final time. And so in principle, this adds to this trivial phase that I have shown before. And then you basically stay in one of these eigenstates. For instance, if you are initially in an eigenstate indexed by m, then you stay in this eigenstate by m. If you that applies to a situation where you slowly evolve in time. And basically this phase here, this additional geometric phase, can in principle be gauged away if there's a gauge degree of freedom. And therefore, it is oftentimes unphysical or unobservable. But there is an exception to this, and that is if you take a closed path in parameter space, and then this space is the well-known Berry phase that you all know.
Sorry, Björn, what is M here? M of R? I'm not sure you.
N of R?
M Madrid in that equation there in blue.
It's just basically so this M of R, you mean, right?
Yeah, that's right.
It's just like the choice of, it's a particular value of n that you have chosen for a particular
as initial problem. Okay, good.
So for instance, if you start in a ground state and then of the system, and then you could say this ground state I give a value of m, and that would be this state.
Okay, thanks.
It's just a particular value of n. That's the shorthand. Okay, now, so this is something that is rather well known. I think the next slides is a bit less well known, and that is what people call adiabatic perturbation theory. Some of you will know who have worked on this, others not. I have also not worked on this before very much. And so, so basically, you ask yourself the question: what happens to adiabatic time evolution, which means you evolve in time, not very quick as compared to inverse energy scales of the problem. And what happens to this if you include some corrections that are, let's say, next order? Yeah? So you evolve now a little bit quicker, and you want to understand in which sense the bare adiabatic time evolution changes. And then you can do something which is called adiabatic perturbation theory, and then you have basically corrections to the eigen values and the eigenvectors. So this is the correction to the eigenvalue, and this is the correction to the eigenvector. And you see, so if my initial state, my ground state, if you wish, was m, as Pablo just asked, then the corrections to this eigenvector will have some transitions to other states, let's say to excited states in the problem if I started in the ground state. And you have some energy denominator. So this looks quite similar to what we know from ordinary perturbation theory. And let's say the small parameter is somehow related to how fast I change, which is related to this r vector dot here, how fast I change in, let's say, the system parameters as a function of time. And basically the difference, which is this energy denominator here, of the energy gaps, or the, let's say, the distance of the ground state to excited states. So now the question is whether there is some kind of a geometrical response in this problem that we can relate to topology, to Berry phases, etc., Berry curvatures. And the answer is yes. That's why I tell it to you. And the geometric response is related to what people call a total energy transfer rate. So you take the Hamiltonian, you take an expectation value of it in some state, and you take the time derivative of it. And so now you can rewrite this, because this is an h of r of t, as an r vector dot times a vector I of r of t. And this vector typically people call current operator. So this is the derivative of the Hamiltonian with respect to its time-dependent parameters in some direction. That's why this is also a vector. And then you can look at the, let's say, a certain index of this vector, which is written here, like the kth index. So now I give the expectation value also an index m, which means I am in the mth band. So this could be, for instance, a ground state, as I said before. And then if I take now the expectation value of this object here and I plug it into this machinery that I explained to you before of the adiabatic time evolution, and I look at, let's say, I consider first order corrections to the problem, then I have two contributions here. First order in R dot, I could say. I have two contributions. One is the basically the energy band EM of R of t divided by dr in k direction of t. And this people call Bloch oscillation contribution. And then there's another one, and this other one has a contribution which has the Barry curvature as an index. So so let's be more specific on the next slide. So the first order corrections to this energy transfer in, or the current operator that corresponds to this energy transfer in k direction, has a contribution which is related to a Barry curvature. And this comes from, let's say, transitions or matrix elements between the ground state, which is my M, and some excited states. And they sandwich this current operator in a certain direction. So here in K and here in Barry directions. And so this is a geometric response, let's say. And it is due to some virtual transitions to the excited states, which can be seen by rewriting this Barry curvature in a slightly different way. So you see that only virtual transitions matter, but this will give rise to a topological response at the end. And I will now explain how this topological response can be understood from a true, let's say, quantum system that we all know very well. So the quantum system I consider is just a single spin. So this is done. There was a very nice paper by Martin, Raphael, and Halperin, and basically this idea is based on this paper. And so this is one can view as a qubit. So this is a spin qubit, and the spin qubit is exposed to a static magnetic field B0, which is chosen in z direction. And it is driven by some kind of time-dependent magnetic fields, which could be some kind of microwave lines that enter this qubit, which give rise to, which should be two frequencies, omega-1 and omega-2, that are incommensurate. Otherwise, if they are commensurate, then this is not a quantum anomalous Hall problem, because it's just a one-dimensional problem. If they're incommensurate, it's somehow in Floquet space a two-dimensional problem. And in a real physical system, this would be the typical ESR, electron spin resonance setup that people have tried to build experimentally to build basically single qubit gates for spin qubit. So now how these magnetic fields look like. So there is this people call quasi-periodic, because it's periodic in each, let's say, field itself. So there's let's say a field B1 and a field B2, which correspond to this driving omega-1 and driving omega-2. And basically in each of these omegas, there is a periodicity. There's a true periodicity, which, let's say, a period of time, which is 2 pi over omega j. But since the two frequencies are incommensurate, there's no true periodicity in the whole system. So therefore, that's what people call quasi-periodic. But this is necessary for this mapping of this problem to the quantum anomalous problem. So what you can do is, there's an alternative way of thinking about this, which is in Floquet space. And in flow K space, you write down the flow K eigenstates, which are written here. So there's typically a flow K energy, epsilon n, and then there's a state which reflects this periodicity in time. And you can Fourier transform this state with respect to this frequencies phi of t. You can also Fourier transform the Hamiltonian. And then you will find kind of something like a tight binding model in flow K space, a time independent problem in flow K space, where you have this Hamiltonian here and you have some kind of contribution which is like a potential on each of these sides. And basically the Hamiltonian reflects that, so each of these sides correspond to a fixed number of photons of M1 type and of M2 type. And with the Hamiltonian, you can jump between these sides, which means you can absorb or emit photons. And this gives rise to something like a potential here that is lying over the whole lattice. And basically by this, you see that if you have an incommensurate frequency, you can map this to a 2D problem. And this 2D problem will be analogous to a quantum anomalous Hall effect, as I will explain soon. Okay, now let's look at the energy transfer rate that I explained before and see how the topological response comes about in this problem. So, so what I do to calculate the energy transfer rate, as I explained before, is I take the time derivative of the Hamiltonian, of the expectation value of the Hamiltonian in some state, typically the ground state. And I can write this now. I have now two contributions because I have this two fields. I have the two directions. And I can write this now as a sum of two terms, an omega-1 contribution and an omega-2 contribution. So omega-1 and omega-2 is like in my previous slides, this R dot in some direction. So I have the sum of these two terms and the current operator by this expression here. And now if I calculate up to first order in this adiabatic perturbation theory, then I get precisely what I wrote before. So now, for instance, if I put myself in the nth band, so now I changed M to N, unfortunately. This should be the ground state, for instance, again. Then I get, for this current, I get two contributions. So I get this Bloch oscillation part, and I get this Berry curvature part. And this you have all seen in these general formulas before. Now we have to find, let's say, the way to see the topological response in this problem. So, and that comes on this slide. So there is.
So yes? Björn, can I maybe stop you for a second? So before you defined the Berry curvature in terms of the I operators, and now it's the more traditional connection or Berry curvature with the derivatives of the eigenstates. Did I miss something?
I think it's equivalent because
it's totally equivalent.
Yeah, because if you go back to the slide where both. Here you see that, I mean, these I operators are like DH.
Oh, they're the same.
Phi, right? And then you can always use this that you basically pull out the DH and then act with the H on some of these ends, and then you get rid of this.
Got it.
Here, and at the end you have something like this.
Okay. Okay, great. Thanks.
You know this, right?
Yeah.
I think it's equivalent. It's just that
it's written in
I operators are this DH, D phi. Right?
Yeah. Okay.
DH, D arc.
Got it.
Okay.
Thanks.
And the other form is shorter. This one. Okay. So now I was explaining you about the topological response. So basically, I have in this expression still here, I have this sum of two energy pumping rates. So these are my energy pumping rates. So I have omega-1, I1, and omega-2, I2 in a given band n. And now what I do is I take like a time average of it, a long time average. So I start from my initial time 0. I average this rate until a time t, and I divide by the time window 1 over t. And if I take this limit if I take this in the limit t going to infinity, then because I have these two incommensurate frequencies, I will basically end up at every point in this space, in this let's say Floquet space of this frequencies phi, and I will just integrate over any possible value of phi up, and I have a prefactor omega k over 2 pi. And if I do this, so if I investigate this carefully, then I can show that I have, let's say, two type of average pumping rates. Now this is a time average pumping rates because I average over time, and I have one which is like a pumping rate from the field 1 to the field 2, and I have another one which is the pumping rate from the field 2 to the field 1, and they exactly compensate each other. So one is exactly the opposite to the other one, and they are given by a topological response, because they are given by a Chern number which corresponds to the Chern number of this nth band, defined in a regular way, times 1 over pi times omega 1 times omega 2. And this is what people call a topological frequency conversion. And you can interpret it in, let's say, in the very same way as we all know from other kind of topological problems of this kind, that you can write the Hamiltonian basically as some d vector times a spin, and the d vector has this form where there's a sine of phi. These are now these frequencies, sine of phi 1, sine of phi 2, m minus cosine of phi 1, cosine of phi 2. And now if this m is larger than 2, then you are always in the trivial regime. So this picture here is for, wrote down somewhere, this m 2.2. And so this is in the trivial regime. Then basically I cannot cover the whole sphere of this with this vector d, because my z component is always dominated by m. And if this m is smaller than 2, then basically the cosines here, they can win against the m under certain conditions. This is shown in the lower part here. And in this particular problem, you only have Chern number 0 or plus minus 1. That's what you get. And now you can basically look at numerical simulations. So you can, so there's a phase transition at m equal 2, which you have seen, and you can, for instance, calculate this energy transfer rates, and you can also calculate the average of it. And you see that if you are in a topological phase, then this energy, there's always shown the one and the other one. So the one is minus the other one. There's this small oscillations on top of the big ones, and the small ones comes from this Bloch oscillations, and the big ones are basically the Berry curvature part of it. And if you get closer to the phase transition, it becomes very messy, and which is here shown close to 2. And if you are above the phase transition, if you come to larger values of m, then you have just no slope here anymore, just a straight line. And so physically, this means that you shift photons from the one drive to the other one on average, in a, let's say, locked sense, in a topological sense. And this is done via the spin. The spin is the mediator of transferring photons from one drive to another drive. And there were experiments that looked at this problem. So there was one by Martinez Group a long time ago. So they are able to build their own superconducting qubits. And these guys, they are theorists. They use this IBM quantum computer. They don't build their own lab. They just applied it to this. And so basically they looked at the similar problem, and what they looked at is they now said, okay, we don't take a real spin, but we take a superconducting qubit. So we take the qubit states of the superconducting qubit. We change basically some parameters in our Hamiltonian in some periodic fashion, and we look at how the eigenstates change. We looked at this first order correction through adiabatic perturbation theory. And they really did some quantum state tomography very carefully, and then basically tried to find a signature of this Chern number by integrating over, let's say, a full trajectory. And they found something close to 1. And these guys, they did something similar based on this IBM quantum computer, and they also find something similar. So in principle, this can be done. It's a bit difficult to basically measure directly this energy transfer. That's why you typically measure properties of your qubit and then infer this energy transfer from the certain operators that are defined at the level of the qubit, which is much easier to measure. Okay, now we turn to, let's say, a slight extension of this problem, but with a big impact, let's say, with a big difference or a big bit added value, which I call interacting topological frequency converter. And so in the interacting topological frequency converter, the way we defined it, I have two spins now, and they are both experience the same static magnetic field and the same two incommensurate driven fields. And additionally to this, these two qubits, they can interact in an anisotropic fashion. So I have a Jx, Jy, and Jz. And I want to understand in which sense this interaction can change this topological response. That's my aim. And so there is the Hamiltonian commutes with the total spin. So the total spin is a good quantum number. And so there is a singlet space and a triplet space. And the singlet space is just a single state. So its dynamics is boring. It will just stay in the same state. And the triplet space is exciting. So we focus on the triplet space, because the triplet space has non-trivial dynamics. And so now here's the Hamiltonian I can write down for the triplet space, and I have triplet eigenstates. So for instance, this psi1, 1 is like up, up, and this psi1 minus 1 is down, down, and this psi1, 0 is 1 over square root of 2, up, down, plus, down, up. And you see that now it matters that there's an anisotropy problem. This is kind of crucial. If it's isotropic, it's again a bit trivial and not so exciting. So we want to have a little bit anisotropy in this interaction. It's not necessarily to be at a specific point. What is more important is that basically the energy gaps of the problem are large enough that quasi-adiabatic time evolution is, let's say, a proper assumption of the problem. And then we have now the interplay between the B field and the interaction in the problem. And so we choose a particular point, but just for simplicity, let's say that Jx equals Jy, but Jz is different to Jx and Jy. And so this means that this J bar, which I think is this J curly here, because I didn't get the curly here in my way I write the formulas. And so this J bar should be finite. If they are all the same, it's 0. So I want this J bar to be finite. And then I have some points, some high symmetry points in the problem, which are points of these phases. So for instance, if these two phases are 0, if one is 0, one is pi, one is pi, one is 0, or both of them are pi. And then I will see topological phase transitions for certain choices of this Jz bar, which is the same as this curly Jz. So for instance, I see a topological phase transition at 0, 0, if this Jz is plus minus the modulus of 2 minus m. M is B0 over BC, and B0 was the static electric field, and C was the field that corresponds to the circular polarized drive. And so now you see a topological phase diagram, and it's a bit busy, the slide, but I will explain it carefully to you. So this is the ground state. This is the first excited state. This is the second excited state, and they will change because now I play around with Jz and I have a certain choice of B, and so it's not always something like that. So this T plus and in the triplet space, T plus, T minus, or T0 can be the ground state depending on certain parameter choice. But you see something funny in this plot. So if you had the problem of two spins that were non-interacting, and you drive them with the same magnetic field, then you could only have even Chern numbers, because you do exactly the same to the one spin as you do to the other spin. So you could have Chern number 0, Chern number 2, maybe Chern number 4 if there was 4 possible, or minus 2. But now in this problem, I see something funny, because now in the presence of interactions, I get, for instance, odd chair numbers. Yeah? I get a chair number 1, for instance, here, and I get a chair number -1 here. Or I get even chair numbers that are higher, that are larger than just the sum of the two non-interacting ones, which is this region. Unfortunately, these guys I only get in excited states and not in ground states. But I get them. So these are two interesting features, and we try to understand the physics behind it. It's not so easy. It has a bit to do with, let's say, entanglement. So this slide is also a bit busy, but maybe I can explain you just one corner of it. So this, I think the first row is for the ground state, and the second row is for the first excited state. So let's focus on the ground state. So in the ground state, I, for instance, have a chair number 2 if, let's say, at the high symmetry points, so at 0, 0, at pi, pi, at 0, pi, and pi 0, I have the configurations, ground state configurations that are different in terms of the spins pointing in space. So for instance, at 0, 0, I have up, up, and at pi, pi, I have down, down, and at 0, pi, and pi 0, I have down, down. Under this condition, I have something similar to the two copies of the, let's say, the single spin case in the absence of interaction. Because in the absence of interactions, I can never get the T0, the 1 over square root of 2 up, down, plus down, up as a ground state. Now, if I turn on interactions, then this can happen. And so, for instance, for the C = 1 case, this happens. And then I have at this position, I have, let's say, this entangled ground state. And on these positions, I have the same as before. And under this condition, I get a chair number = 1. And maybe you can view it in some sense as that one spin can rotate from up to down, but the other one not, because the other one is basically down all the time. But it's not a good picture. So we never developed a really good picture, especially when you go now to high chair numbers, like this one here, for instance, C = 3. Then you have this weird configuration where you have here up, up, here down, down, and here the entangled state. And it's, in some sense, it's just an observation that whenever you see something interesting, something that is unusual in this problem, it has to do with the appearance of this ground state that is at some high symmetry points that is cannot be a ground state in the non-interacting scenario. And then you can do similar numerical analysis as we have done before, and you find also by this numerics that they are stable, let's say, quantized energy transfer rates on average. And there's always some regimes where they are not quantized, because that is the regimes where the gaps are very small and they have strong diabatic contributions. Okay, so now I turn to the last part, which is topological burning glass effect, and it gives another twist to this problem. And so what I do now is the following. I take a system which is a central spin, and so this is one spin that is subjected to this magnetic field that I discussed the whole time through the talk. And so there's a static contribution, B0, and two driven contributions with different frequency. And this is surrounded by other spins that are not driven by this magnetic field. So in some sense, this is like a let's say ESR experiment where you drive an electron spin. If you are on resonance with some properties of an electron spin, and you have surrounded nuclear spins, and they are coupled to the electron spin by the so-called hyperfine interaction. And now the question is, in this setup, what happens to this topological frequency conversion? What is the role of the outer spins, of the bar spins to the top? And for simplicity, we couple all the bar spins by the same coupling constant A, which is not necessary. It just makes the problem easier to calculate. If we have also done some numerical simulations where we do not take the same couplings, and then again, what always matters in this problem is how large are the energy scales of the interacting system with respect to the driving. And as long as there are substantial gaps, then the system doesn't care. It behaves as if the coupling was constant. And if you start to close gaps and so on, then it becomes much more difficult and complicated, because then you have all these diabatic transitions that bring you away from a quantized response. So on this problem, as we have chosen it here, there's the Hamiltonian commutes with J, with the total spin of the Bass spins, and so we choose one particular J value of the eigenvalue of J squared for the next type of discussions. So now what you have to understand better to see to understand the physics of this burning glass effect is how the spectrum of this big system, the big quantum system, changed. So the central spin and all the Bass spins change if you change the coupling between the center spin and the Bass spins. So if the coupling is zero, then basically you have just two sets of states, one with plus 1/2, one with minus 1/2. This is in some kind of units of this E vector. And if you turn on the coupling, then you basically lift the degeneracy of this set of states. First you lift it slightly, and then you lift it rather in a more pronounced way. And the difference, what is important, so later on we will move from here to here and discuss basically how the topological burning glass effect is affected by this. And what you see now, for instance, if I put myself into the ground state of this problem here, then the next excited state has an energy difference which scales like 1/n. This is somehow a bug of this model, because as I told you on the very first slide, we have an enhancement of the topological response by a factor n, which is nice. It's like an amplifier of topology. But the drawback is that basically the distance of states scales like 1/n. So which means that it's really just an intermediate n effect. So if you make n very large, then the distance here becomes very small, and then it will be very difficult to do some adiabatic time evolution, because you want to evolve slower than the distance to the next level. And so basically this only happens at intermediate values of n. That's how it is. That's the physics of the problem. So now you can do just the very same thing I did before, but you now get the interesting twist by thinking about non-unitary dynamics and the influence of this Bass spins. So the point is that the operator that depends on time, which is the time-dependent magnetic field in this problem, only acts on the central spin. So this means if I now look at my energy transfer rate that I discussed throughout the talk, and I calculate now this expectation value of this current operator in k direction, then I can do this by taking the trace over the central spin, which I call trace 0, of the reduced density matrix with respect to, so I traced it for this reduced density matrix, I traced out the Bass degrees of freedom, convoluted with this current operator. And so in the reduced density, I have some adiabatic time evolution part, and I have some kind of next order in adiabatic perturbation theory part, which again takes into account a coupling from the state beta, which is now my ground state, to some other excited states alpha. And basically this coupling, so if you think about it in terms of, let's say, reduced density matrix physics, if I stay in my state and I do really adiabatic time evolution, and I'm, for instance, in the ground state and all spins are polarized, then I can take the reduced density matrix of this problem, and then I have just the density matrix of a single spin, and I can only have a Chern number 1 and not a Chern number n in this problem. So I need really the states, the diabatic states of the whole problem to see an enhancement of the Chern number. That's the crucial aspect of this problem. So I can write down the reduced density matrix in a form like this, where I have an adiabatic part and a, let's say, diabatic part. And the adiabatic part can max give me a chair number 1, not a chair number n. And so this part here, which comes from basically the non-unitary elements of dynamics, will give me my chair number n. So this is what I just said. The adiabatic part, if I start in the ground state of the problem where all spins point in one direction, give me the single spin topology, and the non-unitary dynamics, which come from the coupling to the environment, give me the n spin topology. And so this you can also analyze now. So this is, we plot now this time average energy transfer rate, one of them, for changing the frequency omega and changing the coupling A. And you see that there are, let's say, 3 distinct colors in this problem. This is now for n equal 5, for instance. There's a color red, which corresponds to the pumping rate with the chair number 5. There's a color blue, which corresponds to a chair number 1. And there's a color white, which corresponds to chair number 0. And so the red means I am in the ground state. I drive the system a little bit. I can see this effect quite pronounced from the beginning on. And I see this high chair number. The blue is also a funny regime. The blue is like a pre-thermalization regime. If you go back to the here to the spectrum. So the blue is a regime where basically you thermalize the system in this lower set of states and not yet in this upper set of states. And if you do this, then you can have a chair number 1 situation, which happens at intermediate frequencies, which is like a diabatic quantized response. That's also funny in general, which comes from this particular problem. I mean, it will change. It will be more difficult if you don't couple equally all spins and so on. But in this particular problem with this symmetry, it's a funny limit. Okay, so this brings me to the end of my talk. So thanks a lot for your attention. So I started with explaining to you the quantum dynamics in parameter space. Then I explained this topological frequency conversion problem on the basis of single spin, which is, let's say, a dynamic and analog of the quantum anomalous Hall effect. And then I turned to the interacting topological frequency conversion, where you can have chair numbers that are not only even, but also odd, and even chair numbers that are larger than the number of constituents. So like 3 for 2 spins, or we also looked at 3 spins, and you can have up to 5. And so this only happens in excited states, so that's why it's a bit difficult to observe. And then I explained to you the topological burning glass effect, where basically the central spin inherits the chair number of the outer spins under certain conditions. So thank you very much for your attention. You are muted.
Yes, sorry. Thank you very much, Jon. Great, amazing talk. So let me see if there's any questions in the audience. Well, it usually takes a bit for people to get started. So I take the chance to start myself. So I have a couple of questions. So starting from the end, this phase diagram, parameter phase diagram that you showed us for n equal 5, imagine you go to the physically natural limit of large n. So you mentioned your mini gap is going to shrink. So the red region is going to really become very small, right?
Yes.
So everything becomes just blue and white in that case, right?
Yes.
Okay,
yes.
okay, great. That's
and I think the blue is still somehow extended. But maybe also the blue gets, because then I think all the levels will become equally distant. So and basically if you sum of all chair numbers, it's 0, right? And so then the question is whether you have some intermediate regime where you do not get sum over all numbers.
Right. So the asymptote between white and red also goes down to 0. So the large A blue region it disappears also, right? That's what you're saying.
Yeah, this I don't know actually. It's a good question.
Okay.
Whether there is, I mean, in the large n limit, maybe it's only y. But
so
it,
that would,
but it sounds weird that it's only y, because somehow the frequency has to be large enough to explore the whole states, all states, right?
Yeah. So on the other hand, it would.
When we go back to the. But everything is proportional to 1 over n.
Right. So
I don't know. I have to think about it. What I mean, your question is basically. I mean, I'm very sure that the red region will disappear. Okay. That's we all agree on. And I think your question is what happens in the very large n limit to the blue, and the white region will be for sure there at some point.
But it's clear that in the finite n case, like in this plot, the blue region shrinks to 0 at large A, right?
Yeah.
Or that's not. Yeah. It doesn't depend on B0. So that goes to 0 essentially.
Yes.
So the only possibility.
This is done for a certain choice of B0, but if you increase A, then at some point the B doesn't matter. Okay, got it. Okay, so and I have another question that was intriguing. So I like the mapping between the 2D Floquet with finite Chern number and the idea that it's equivalent to a quantum Hall phase, but I didn't quite get how things map in the two cases. So is there an analog of this power transfer, of this energy transfer rate in the quantum Hall effect that helps us understand? Yeah, I think it's just the conductivity, but I think the easiest way is like this, right? So that if you think about let's say the quantum anomalous Hall effect as one block of the Beenakker-Sang model, right? And so then if you look at in the Beenakker-Sang model, you have these two blocks, but if you just look at one block of them, then basically this corresponds to a quantum anomalous Hall effect with the Chern number, right? And then here and this can be written as a Hamiltonian h of k is E of k times some Pauli matrix sigma, which in this Beenakker-Sang model are some EH states of Merkur-Telluride quantum worlds, for instance. Mm-hmm. And then here you have this sine k, let's say kx,
right,
ky, and here you have this m minus cosine kx, cosine ky, right? And basically what is k in the Brüder zone is now frequencies in my dynamical problem, mm-hmm. And the problem maps in the sense of h equal d times s exactly on each other. Mm-hmm. And then the response, this is maybe the question you had about basically the response in the like here in the Beenakker-Sang or in the quantum anomalous Hall model would be a quantized mm-hmm. Conductivity or conductance, right? And maybe one sees it. One sees this actually is a bit hidden, so we have to take this energy transfer rate, we have to integrate over time and divide by 1 over t, and then only then we get a response which is a Chern number that is equivalent to this conductivity.
Right.
Because this is essential here, that you basically integrate over the whole phase space.
Yeah. Mm-hmm. Right. Okay, so then since there's still no questions, I take a chance to ask a third question to you. So you said it very clearly at the beginning. So this mapping to 2D Floquet space makes sense for incommensurate frequencies. So something dramatic must happen to the problem if you go to commensurate frequencies. The problem should become 1D suddenly. Mm-hmm, mm-hmm. How does that work? So you're in a Chern number, finite Chern number, and then you tweak your frequency a bit, and suddenly the problem is different. How does that work?
I think it should be similar to here, right? That somehow here it's also when you are close to this phase transition, then like close to 2, then everything that is kind of topological, which in this sense here is a clear slope. Yeah?
Right.
It's kind of washed out. You have lots of transitions between states, and
okay, so you're saying
you get a mess basically, yeah. And I think this will
okay.
be similar if you now change these frequencies in such a way that they are commensurate. Then you will have a new structure in, let's say, this spectrum, which is then 1D type of structure, but you can still play around with these things, of course. And then I guess you will have no possibility to get any quantized or, let's say, constant slope stuff anymore, but you see a mess. But I think it's a good question. We have never done it in, like, numerically. You could easily do it, right? We have always, typically we take the golden ratio between omega-1 and omega-2. Yeah.
Right. We have a question by Alfredo.
Yes, you can unmute yourself. I already.
Okay.
Okay. Hi, Björn. Thank you for. I found it very interesting, and I was all the time wondering about the possible physical realization. And well, I think you're thinking of spin qubits or
yeah, I think the field lacks a nice realization. So that's why it's maybe, I think it's very nice for students, for instance, to learn a lot about this adiabatic perturbation theory and diabatic corrections, and you can do lots of things analytically. It's very nice, actually. But I think the field in general lacks a little bit interesting impact on, let's say, two experiments. I think here what the people did is, I mean, especially on the left side, on the right side, they did it slightly different. On the left side, what they did is that they really did, they're very, very, as you know, they are very, very good at controlling their spin qubits, which in this or their qubits, in this case is a superconducting qubit. And they really did a very, very careful state tomography. Yeah? And then basically they made this measurement here of some expectation value as a function of time, and they integrated over this shaded areas here, and by this they showed that this is a quantized response if you integrate over all the shaded areas. And what it means physically is that you somehow pump photons on average from the one thing to the other thing. This is funny, right? Because they are incommensurate. It's not so easy to pump a photon of the omega-1 type to the omega-2 type. Yeah? It's not just you take two of these guys and you get one of the other one or so, but you really need the spin in the middle basically help you to fix this incommensurability, right?
I see.
That's cool. That's funny, right? But it only happens on average. It doesn't happen. It goes like back and forth, and so it doesn't happen all the time that you can pump photons from the one side to the other. It just happens a little bit here, a little bit there, and in this sense, it's a bit boring, I think, in terms of let's say some kind of application, some experimental impact.
It's an academic interest, but on the other hand, to address an experiment, you would need to take into account dissipation. You are not including it in the theory. How it would
maybe
affect.
If you are like a Saclay type of experimentalist, and you have really a strong control on not only on your qubit but also on, let's say, the driving and so on. That could be an interesting aspect of the problem, whether this has some experimental, let's say, impact that has not been considered yet. I mean, these guys they do differently, right? They basically measure precisely how this kind of first correction to adiabatic time evolution affect their spin, and then they can affect their qubit, and then they can calculate observables with respect to this state that tells them about this energy transfer rate, but they do not need to measure any kind of energy in the two driving fields. They just need to measure the qubit, which makes sense. If if this contains all the information. But if you think more about the more interesting application of this, in the sense of that, I mean, it would be nice if you had two microwave drivings and they are incommensurate, and actually it's very difficult to let them talk to each other, and you now found a way to mediate between them also, right?
Yeah, you need a cavity or some kind of
it's somehow the spin is something like the mediator.
Okay. Thank you, Björn. Thank you.
Thanks.
Okay, we have another question. Go ahead.
Yeah, hi Björn. Again, thanks for your nice talk. I just have a bit more technical question. I don't know if it makes sense. So when you explained us in the beginning this let's say theory of adiabatic perturbation theory, I think it's important that you don't have degeneracies, right? I think.
Yeah. This I assumed. Yeah, I think it's important that I don't have degeneracies in the state where I start from. Let's call it the ground state.
Yeah.
But I think I can have degeneracies in the excited state. This is probably
yes. Yeah. No, yes, I agree. Yes. But my question is actually in the last part of your talk with the many spins. So this spin bath, let's call it spin bath, is not in the magnetic field, right? So the spin bath has a huge degeneracy. So is this important, or is only important that the central spin is not degenerate, so that the states there are not degenerate?
I think I lift this degeneracy if I turn on A, right?
Okay.
So the degeneracy you are talking about is for A equals 0, right?
Okay.
And then if I turn on A, then basically the central spin acts like a magnetic field for the other spins. And that's
okay.
why.
So you say you remove, so you say the total Hamiltonian with a finite A removes all the degeneracies.
Yes.
Okay. Thanks.
Even if A is equal for all couplings? So all the couplings are the same?
Say again?
Even if all couplings A are the same. So A will remove all degeneracies automatically.
I think so. I think because I guess all these states at the end when A is large are all singly degenerate. Maybe there is some additional degeneracy between the states
I mean,
of different J, right? Because what I plot here is I choose a particular value of the quantum number of the J square, right? Of the total angular momentum operator. And I plot this spectrum for a choice of J. And the Hamiltonian does not couple to the other sectors, right? But maybe if I plot them all on top of each other, I will pick up some degeneracies, but I think as long as the Hamiltonian doesn't couple them, it doesn't matter, right? But if I change now, then if I change this coupling A to the different spins, then I lose this this property that the small j, so the eigenvalue of J square is the good quantum number, right? And then this might matter. Can you follow me? What I mean? So at the moment, for this Hamiltonian here, I choose the same A for the coupling of the central spin to all nuclear spins. Okay, this is a bit unphysical, because in the true quantum system, the hyperfine interaction will depend on the distance of this guy to this guy, for instance. Right? So it's more natural that they are not coupled all in the same way, but there's some kind of range also of the coupling. Right? And then if I write down this, then this property doesn't hold anymore. Right? Then the Hamiltonian does not commute anymore with J square. And then basically all the sectors, at the moment I can choose a certain sector of J square, like one particular eigenvalue of it, because there's a block structure of this Hamiltonian, and they will not talk to each other. But if I get rid of this, then I have to be more careful.
But Björn, I mean, let's say this Hamiltonian you have at this slide, so A times S0 times J, and so you say J squared is a good quantum number, yes? So each J quantum number has a different energy. Mm-hmm. I agree, but there is a degeneracy in, so you also have, let me see, so there's also JZ or something.
Yeah, like yeah, and this JZ is somehow kind of here. I mean, in the next slide. So if the magnetic field doesn't couple, if A is 0 and the magnetic field doesn't couple to the nuclear spins, then basically I have, as you pointed out, I have this strong degeneracy of this level at -1/2 and at +1/2. Because all the nuclear spins have the same energy. Yeah? But as soon as I turn on A, I lift this degeneracy of this MJ quantum numbers.
Oh, okay. You say because the central spin is not degenerate in non-zero field, that's lifting also this degeneracy.
Yeah, because the central spin couples to the magnetic field, right?
Okay.
To the static.
Okay. Thanks a lot. Okay.
More questions? Okay. No questions on the chat or?
Okay, great. So I think we are